Hey, good morning, everyone. I'm Hueta from University of Denver. Now I'm on sabbatical leave at ISAS, JAXA, home of Japanese space mission. So thank you for the honor for letting me to speak here. I'm very fond of this meeting because I made a debut at the FN2 meeting. So that makes me feel old, but that's another story. Let's begin. Look at this side. Okay, so the reason why we are here is to talk about the morphologies of these objects, and then here's the HR diagram, and then as we all know, these guys start with something spherical, and then they end up messed up. So we need to figure out how they mess up their structures, and then the conventional wisdom is that we look at these guys in between, and then that's what Margaret Meixner and I did for event 2. And then by looking at warm dust, and then these warm dust grains seem to be forming some sort of equatorial enhancement around the star. And so by the time these guys get to post-AGB phase, they seem to have already developed some sort of, at least something that you can describe as equatorial enhancement. So they have already departed from the spherical symmetry. So what do you do? You can either look at younger ones to look for the onset of this structural development, or and then I have for my student Rebecca Rattray has a poster B14, and then my poster B33. So you can look at those two, and then also you can look at these guys, old guys, and then look at the extended part of the shell to look for the records, fossil records of this structural development in the density distribution of this extended part of the nebulosity. And then my other student, Rachel Tomasino, has a poster B31. Now, so here is the cartoon of Hueta nebula here. So the central side is here, and then here's the inner radius, and the outer radius here, and ISM. And then we can sort of have this very naive, stratified view of the structure. So inside, because of the radiation from the central star, we have fully ionized region, and then outside a little bit partially ionized, and then neutral region, and this is where you start seeing some dust, and then molecular region, and then yet another neutral region for the dissociation region because of the intercellular fields that is coming in from the outside. So this is a naive view of this simple stratified structure. And when we talk about quantum nebulae, so this is HFC image of cat side, and this blue here is X-ray, and Rudy failed to show the point source in the middle, but you see the point source there. So that's for Rudy. And then when we say quantum nebulae, so we all often think of this kind of bright emission line structure, and that's basically this region. And we have a whole lot more volume outside, and this is the region where you have to use longer wavelengths to probe. So this is the idea of using fine thread to look at this cold region to probe what's happening way back in time. Right, so we want to look at the history of muscles, and then so we use Herschel, which is a 3.5 meter diameter telescope, so the largest telescope in fine thread. So, the largest, so the maximum spatial resolution we could ever have. So why not use that for that purpose? And then Herschel carries 3 instruments, PAX, SPIRE, and HiFi, and we used 2 of these, PAX and SPIRE. The HiFi wasn't available at the time, so, and then also HiFi is not good for mapping, so we use PAX and SPIRE. So what we did in this survey is that this is an open time cycle 1 program, and it used 200 hours of Herschel time. So it was actually the 3rd largest program in cycle 1, but we looked at 11 planetary nebulae. So 200 hours, 11, so it doesn't match up, it doesn't, mass doesn't match up. But then this is with you how difficult this is to get the surface brightness, to detect the surface brightness of extended objects. And then so the main purpose is that we want to spatially resolve and then look at spatial variation of thermal continuum. And that will give us idea of dust grains, how dust grains are distributed, and then we can look at also finite lines, and then that will tell us something about the gas. So we can look at the dust component, gas component observation at the same time, and then we can combine these two. And then one of the things that we want to do is from the dust properties we get the mass of the dust, again spatially resolved, and then from the property of gas we get the gas, the mass of the gas, again spatially resolved, and then we combine the two, and then we can get, for example, gas to dust mass ratio in spatially resolved manner. And that's something that has been done early. So that was one of the things that we wanted to do. And these are the targets. And you can look at this later. And I'm going to run out of time. I'm sure 100% positive I'm going to run out of time. So I'm going to show you summary first. So the hot plants, their product are almost ready. Then I'm going to show you one example by using this one object, NZC6781. And highlights, we detected OH plus in 3 negative in power plants, but then I'm going to show you just for this object. And then there was a simultaneous discovery of OH plus from other group, Maslow's of the Gold Stars group. And then they found 2, so that makes total of 5 PMs. In which OH plus in emission was detected. And then second highlight, so using the broadband maps, we try to understand the dust distribution, and then we get the dust temperature map, and dust emissivity index map, and optical depth map. And these maps will give us the dust mass map, and then total mass to be about 0.004 solar. And then also the gas side. So from the line observations, we make line maps, and then we took the line ratios, and so forth, and then we obtained the empirical gas distribution maps, and then that ended up about this mass, so 0.8 solar mass gas, and if you compare these two, it's about 200 gas to dust mass ratio, and that's for the whole volume. But then we look at the spatially distributed dust maps and the gas maps, then the value of gas to dust ratio varies a lot, from 400 to 30 over the dust shell. So we typically pick one number of gas to dust mass ratio and use it for variety of reasons, but is it good? Maybe not. And it's just one object, and we have 10 other objects to look at, so we will be able to say something about that in pretty soon. Okay, so that's a summary. So let's get to the summary. So the global mapping, essentially, so these are the arbiters of Parkes and Spire. We scan sky orthogonally in 2 directions. Then here's the 5 bands: 70, 160, 250, 350, and 500 micron. The respective beam sizes, and then pixel scales. And Parkes spectroscopy, so we wanted to make a complete map out of it, but the time is short, so we wanted to do that, so we just picked out some of the locations to look at, and then each box represents 5 by 5 spark cell coverage, so here's the broad. So you have 5 spark cells, in total 25, and then we usually make multiple pointings to make observations. And then this 5 by 5 spark cell covers about 50 or 47 second by 47 seconds size of the sky, and then covers 51 micron to 210. And then respective beam sizes in the spectral range is from 10 to 13 seconds. And then this is the chop node observation. So from the chop node positions, you can get the sky, and then sky gets subtracted. And Spire observation, the same story. We point Spire arbiter to the same location where we take the Parkes data. And also the fire observation doesn't include sky. And the idea is that there are lots of kilometers, and then you get outside kilometer data to sky. But our sources are extended, so we need our own sky observation. So we did sky observation at the location of the Pax chart position in order to get the sky whole spectral coverage of the same sky. And here's some information: spectral coverage, number of kilometers, and beam sizes. Okay, again, so the data products, we looked at 11 front-end. Then we got broader maps in general 5 bands. Sometimes we get extra 100 microband, but basically 55 maps for given objects. And then we get the spectra, the total number is 2,740 spectra of these kilometers and spark cells. And then here are some of the sensitivities. And then here's one other thing I should mention here is that at some locations, spark cell and then spire kilometer overlaps spatially. And then for one pointing, at least 7 positions, we have overlap, and then we have complete coverage from 51 up to 672 microns. So here is the broadband images. Here's the N2 in off-stop, and this is 70, 160, 250, 350, 500, resolving this ring structure. This is actually almost colon bipolar nebula. And that structure like this. This is taken from Schwarzman table 6. But this is going to be talked about by Jajela Zhao next to me from Skip. This. So more is coming in the next talk. But one thing I should mention here is that using these 5 band maps, you can actually fit this kind of modified black body, and then pick the emissivity index and the dust temperature, and then you get the temperature map like this, and the temperature being the lowest is about 30K, and then highest here is 42, and this region actually corresponds to the region. So this image is all 3 obstacles. So the highest dust, or the dust of highest temperature, delineates the region of the strongest of the emissions. So this makes sense. And then we get the dust emissivity index map, and then this is almost green here. Green corresponds to 1. So that indicates that the dust species is basically amorphous carbon. And that gives us an idea of opacity of this dust range, and that will help us to estimate the amount of dust, the mass of dust. So this image shows you the column density map, dust column density map, and then showing this nice ring structure, which is represented by this almost hollow cylindrical structure. The hollow cylinder, we are looking through the hollow cylinder from the top. Now here is the spectroscopy side. So this is the full coverage from 52 up to 672. Well, the emission, the continuous emission is so low, and so it's going down below the detection limit. So it's something here, but then well, we get the whole spectrum and lots of lines, the forbidden lines, and then the molecular lines. And then we have 2 pointing, so the black line is in the middle, pointing in the middle, and then the gray spectra corresponds to the pointing to this region on the shell. And then one thing I should point out here is that we made a detection of OH plus. So these lines here, and then there's OH doublet here. And this OH plus emission is detected for the first time in front-end nebulae. And then again, this discovery was made simultaneously by the MES group. And so we are trying to submit papers at the same time and publish at the same time to commemorate. Right, and then, well, again, our intention is to spatially resolve these things. And then here, I show this OH doublet and then OH plus emission line at the 5 by 5 spectrum. And then OH doublet comes from here, OH plus comes from here. So this spatial correspondence also helps us to identify the species. Then from the, so here's the spire side, and then spire spectra. The way spectra looks varies depending on where you are. So inside CO is high or a little lower, but then on the ring, CO emission gets higher, and if you go up, it's going to go up and it's going to disappear. This tells us something about the CO, but spire spectral calibration is not complete yet, so I'm not going to say much about this. And then line ratios of the folded lines. So M357 strong in the inner cavity, but goes down as you go out. And then M2 line is not that high in the middle, but then it's going to go up on the rim and then goes down. And then you can get the ratios. And then so out of these observations, we can make line maps. Here's 0352, 88. N2, 122, 105, and so forth. And we can take ratios between these maps. And then talk about electron temperature and electron densities. So here's the 0352 to 88 ratio. And then these ratios, so these transitions correspond to the lowest two of the 5 lowest transitions. And then from this ratio, you can talk about the electron density. So here's the 52 to 88 ratio versus the electron density. You can prove spatial result electron density here, and then that will give us idea of, well, some other ratio will give us the electron temperature, and then we can iterate on to get these values. So I'm running out of time. So and then we can get the profile. So in this case, we have nice radial structure, so we just average and then get the profile. So this is the electron temperature profile, almost flat in the middle, goes up and then subsides. And then electron density profile as well. So in the O3 case, it's almost flat, but in the N2 case, it varies. So in the middle is the lowest, and it goes up and then goes up. And so forth. And then using this electron temperature, electron density profile or distribution, we can get the abundance distribution as well. So here is the relative abundance, ionic abundance to the hydrogen. And then if you look at the relative strengths of these relative abundances, you can actually say that there are 3 stratified ionized regions in a different ionization stage. So this is the highest ionization region, and the second highest, and then lower one. So we can actually spatially resolve different stratified ionized regions. And last thing, so based off of these electron temperature, electron density maps, we can reconstruct gas column mass map here. And then here's again the dust column map, and then we can compare the two and then get the gas to dust mass ratio map that is here. And this is the log of the ratio. So the dust ring is outside here, and then if you look at the numbers, you'll find in the outside of this color distribution, it's about 200. So medium is 196 plus minus 108, but the actual value varies from 30 at the edge and to 400 at the inner edge of this dust ring. So the gas to dust mass ratio varies a lot, even within this dust ring. So using just one number of gas to dust mass ratio may not be such a good thing, but that's something that we will follow up on. Right, again, summary, so I'm not going to repeat. And so we still have more to do. So as I said, spider data flux calibration is not quite complete. We have some issues about the background and instrumental effects, so we will have to get that resolved. And then do these analysis for other objects. Then we still do other things. Line identification is not complete. And then we can also talk about, for example, 12-0, 13-0 ratio. And then we need to do, think about the X-ray connection, which is already suggested by the detection of OH+. OH+ emission needs some software X-rays. And then we need to do the model calculation. So the spatial resolution will help us to disentangle the degeneracy in the plane of the sky. But what we measure is the whole integrated